right, good morning everyone. Hope you're enjoying your first free coffee for the day. So I'm going to talk about geometric algebra transformers, which indeed is the latest and greatest in geometric deep learning. And because this is a broad audience, I'll introduce the general topic a little bit before diving into our latest work. So this is the Geometric Algebra Transformers paper is joint work with my brilliant colleagues Jan Bremer, Pim de Haan, joint first authors, and Soenke Behrens and myself. Okay, so geometric deep learning is all about applying deep learning to geometric data. So why are we interested in that? Well, there are many applications. So here you see a molecule, and over the last few years, a lot of people have become interested in using machine learning to predict properties of molecules. In principle, quantum mechanics should tell you everything you'd ever want to know about the properties of a molecule, but those computations can be very compute intensive. And so what people do is they use machine learning models to take as input a molecule and predict properties. Can be used for materials design, can be used for drug design if you want to know whether some molecule will bind to a receptor, that kind of thing. So people use machine learning for this. Clearly a geometric object made of, atoms positioned in space and bound to other atoms by bonds. Then you have climate and weather science. So here we have the spherical geometry of the Earth, and you have geometric quantities like vectors, arrows, pointing in the direction that the wind is going, and other variables like pressure and temperature. So also another kind of geometric data. Then there's robotics. So more and more people are trying to use machine learning for robotics to have, in classical robotics, people use control methods and basically pre-program exactly what the robot has to do. And it can be very useful in a factory where it always has to do exactly the same thing. But it would be much nicer if the robot could learn by itself to perform tasks and do so not just in one highly controlled environment, but flexibly in any environment like us humans can do. And there again, it's a geometric problem. There's objects that have a position orientation in space. There's the configuration of the joints of the robot. There's forces and that you have to apply to the actuators via the actuators. So it also requires geometric reasoning. And then here's a problem that people at Qualcomm are interested in. It's a communications and chip company. Very often when you're sending wireless signals from one point to another, it matters what the geometry of the surrounding rooms are, because that affects the signal propagation. So in the next generation of wireless communication in 6G, there will be a lot of AI used in the sending and receiving of these signals. So again, people are using machine learning for that. So what do all these problems have in common? What makes them uniquely difficult? The key word is symmetries. So all of these problems have symmetries, which means that if you apply a transformation to the data, then the thing you're trying to predict stays invariant or varies along with the transformation. So for example, in the case of the molecule, clearly the chemical properties, excuse me, the chemical properties of the molecule don't change when you shift or rotate the molecule in space. So that's an example of a symmetry, a transformation that leaves something invariant. Now, neural networks don't natively understand this. If you show them an example of a molecule and you say, this is the energy or the force field associated with this molecule, it can learn to predict that. But then if you rotate the molecule, now it doesn't know anymore. It has to generalize. And there are various ways to address that. But one method that's become very popular over the last few years is the design principle of equivariance. We started working on this in 2016 with our paper, Group Equivariant Convolutional Networks. And basically what this says is if you have, let's see, pointer. Yeah. Well, if you have your input space x0, that's, let's say, the space of molecules, or maybe it's a space of images, can be any input space. And you have your neural network F1, or maybe it's just one layer of your neural network, then it should be the case that if you apply a transformation to your input and then apply your network layer, that should be the same as applying your network layer and then applying your transformation. So you see an example here on the right, where in the top you see an image that's undergoing a rotation. And here you see the feature map computed by a convolutional neural network. So the convolutional neural network matches a pattern in the image, a learned pattern, at every position. And as the image is rotating, of course, the resulting feature map that says how much the pattern matches at each position is changing. But what you can see is if you back rotate the feature map to get the stabilized view, it's still undergoing morphing. It's changing as the image is rotating. So what that indicates is that this neuron in the convolutional network is detecting different things depending on the orientation. In one orientation, it might be activating based on grass, and then in another orientation, maybe it's activating for a building. And that is an example of a lack of equivariance. If you make the network equivariant, you see what happens on the bottom in the GCNN. The image rotates, and the resulting feature maps computed by the neural network also undergo rotation. So that's an example of equivariance. So why is that a good idea? Well, equivariance gives a constraint on your neural network layers. Not all network layers are equivariant, but you can constrain them to be equivariant. And when you do that, you reduce the number of parameters in the layer, and therefore you can do more statistically efficient learning. So in other words, you need less examples to get to a certain level of performance. Now, it turns out there are many popular network architectures in deep learning that use this principle either explicitly or implicitly. So the very popular transformer architecture, that's the basis of ChatGPT and many other successful methods, that is inherently permutation equivariant, although for autoregressive language modeling applications, this equivariance is broken. That's another story. But it is intrinsically equivariant. Same for architectures like deep sets, graph neural networks. In a graph, clearly it doesn't matter how you orient or how you order the nodes in a graph. So graph neural networks are also permutation equivariant. Then there are a lot of methods that are equivariant to Euclidean transformations like shifts, translations, rotations. There's spherical CNNs, and there's many other examples besides. Okay, so this is geometric deep learning in general. Now let's talk about GATr, the GA transformer. We abbreviate it as GATr, and here's our mascot. So what's the idea behind this work? So geometric deep learning has really exploded. There's been a lot of activity, and a lot of people have designed custom architectures for different tasks. But what you see outside of geometric deep learning is that there's really a very large convergence with basically the transformer architecture being used for all sorts of tasks, not just language modeling, but also there's vision transformers for images. You can apply them to speech processing, speech generation, transcribing speech, all sorts of applications. Basically, it always works quite well. But it needs to be adapted for geometric data in order to account for the symmetries. So what we set out to do here is to develop a general purpose architecture for geometric data, and one that is scalable as well. So the basic ideas behind this, in order to achieve that generality and scalability, is that we use, first of all, geometric algebra representations. That's a certain way of encoding geometric objects that go into the network as inputs, and that the network uses as intermediate representations and that it produces as outputs. And this is a very general thing. So you can encode not just points, as in, let's say, the atom positions in a molecule, but you can encode all sorts of things in that space. We have equivariance, what I just talked about. It's equivariant to 3D rotations and translations. And we have the transformer architecture, which has been so successful in many areas and has a both very high degree of scalability, can deal with very large amounts of data, and is also efficient. Okay, so let's first talk about geometric algebra. Now, I'm not going to introduce this topic. It's not, give you a full explanation of geometric algebra if you've never seen it before. You won't fully understand. That's okay. It's not a super hard topic. It's like you can think of it as linear algebra 2. But I'm still not going to be able to cover a whole linear algebra course here. But the upshot here is the specific geometric algebra that we use, the projective geometric algebra, gives us a 16-dimensional representation space where in this space there live different kinds of geometric quantities. I'll show you a bit more later. And the space also comes with a geometric product, something that you can use to take two of these 16-dimensional quantities, combine them, and produce another one. And this geometric product allows you to construct objects. So if you have 2 points, you can construct a line, or you can also use it to apply transformations to the objects using one single product. So everything, all of geometry becomes really very simple, just the application of this one geometric product. So what I mentioned on the first line is you can represent different kinds of objects in this space. So there are many geometric algebras, but for the one we use in this paper, you can represent scalar quantities, such as, let's say, the temperature at different positions on Earth. You can represent planes, lines, points, volumes, also other things, but these are just some examples. And what you see on the right, without going into too much detail, is that basically these different types of objects, they just live in different subspaces of the 16-dimensional space. You can also, in the same space, you can encode transformations. So sometimes you want to encode transformations as input. For instance, the motion that a robot makes from one time step to another. That can also be provided as input. And so you can represent reflections, translations, rotations, and things like that, all in one single space, and all operations use this one geometric product. If you want to know more, I highly recommend this book, Geometric Algebra for Computer Science. It's been very useful in computer graphics, and now it's starting to make inroads in machine learning. Also, fundamental physics, this is used under the name of Clifford algebras. Okay, so how do we use geometric algebra in practice? So we have some raw inputs, maybe sensor data coming from our robot. This is then pre-processed to get different kinds of geometric types, points, motions, transformations, etc. They are then embedded in the geometric algebra. So we get our multivectors. Then the neural network is applied that takes multivectors as input and produces multivectors as output. And from that, we then extract the data that we need. For instance, if we're trying to control a robot, we get out the steering commands that go to the robot. Okay, then let's talk a little bit about equivariance. So we have these 16-dimensional quantities, these multivectors, and we have a certain way that transformations act on them using the geometric product. And what we've done is we've developed a number of neural network layers that are equivariant to these transformations. And these are all the components that you need to build a transformer architecture. So first of all, there's linear layers, and it turns out you can see on the figure on the right that the linear layers are actually very constrained. So you really reduce the number of parameters a lot, which is a good thing from the perspective of statistical efficiency. You can learn from little data now, but it also reduces the flexibility. So we also have new geometric layers that use the geometric product, and that increase the expressivity of the architecture. Then transformers also have nonlinearities and normalization layers. We create equivariant variants of those. And finally, there's, of course, the very important attention mechanism in the transformer. That's kind of the key to its success. And so what that does is you have a number of queries and keys. Those are vectors. And the queries are matched to the keys to compute some attention weight for the network to figure out what pieces of the data it should attend to. Now, the key thing is that this matching is done with an inner product. And it turns out that in order to make that operation, the whole attention operation equivariant, you need to make the inner product invariant. And magically, geometric algebra provides us with such an invariant inner product. Now, if that's all sounds like mumbo jumbo, don't worry. The upshot is that geometric algebra and transformers, they fit very well together. There's a very nice way to make a transformer equivariant, the attention part. All right, so let's talk about the overall transformer architecture. So here we have a schematic picture. So transformer architecture typically starts with a linear map. In our case, that's an equivariant linear map, followed by some layer norm, more equivariant linear maps. Then there's an attention, which is now our geometric attention, linear maps, then a residual connection. So the input is added back to the output, followed by more of the same. And the whole thing is then repeated for n times if you want to make a deep network with n blocks. All right, so I think I've said most of this. Okay, so those are the main components, the main ideas behind the architecture. Let's look at some results. So we start with a very simple toy experiment just to highlight some of the, well, first of all, for ourselves to test that everything is working, but also to highlight some of the nice properties of this architecture. So in this task, we just start with some points in space, and they are basically point masses that are moving through space. So we have positions, we have velocities, and we have masses. And we just let this system evolve under Newtonian gravity. So it's you could think of them as planets and stars. And this is a notoriously difficult thing to simulate using the classical laws. So we try to see if our network can learn to predict it. So we train on a data set of varying sizes, starting with small data set and then increasingly larger. And we test on a held-out test set. And here we compare a number of different methods. On the left-hand side in this plot, you see on the x-axis the size of the training data set. So as you add more data, of course, the results will get better and better. And on the y-axis, you see the mean absolute error. So lower is better. You want to have low error in predicting the positions. And what you see is that the green curve, that's the GATr architecture, the GA transformer, after only 100 samples, it's already achieved a very low loss. So that shows you the statistical efficiency of incorporating, geometric prior knowledge via equivariance and also via the geometric product, which encodes useful geometric computations that you can do to this data. You see other methods. Some equivariant ones, baselines in blue, that also do quite well, and then a non-equivariant method such as a transformer. And what you see is the transformer starts off with quite a high error. Training a big transformer on 100 data points is usually not advisable. And then as you add more and more and more data, eventually it also gets quite good performance. Here at 10,000 or 100,000 samples, that is still not quite there, which tells you, you really get a big gain from incorporating equivariance. Eventually, it will get there, but often in these kind of scientific applications, getting data is actually quite expensive. You can't just download tons of it from the internet. Then we have another experiment here in the middle plot, where we generalize the number of objects that are in the data. So you might train with 3 stars, and then or 3 planets, and then you add a bunch more. And you see the performance degrades a bit, but it still basically works quite well. And for some of the baselines, like an MLP, it can't deal with that. But the transformer has the property that it can deal with that. Just like in text-based autoregressive models, ChatGPT, you can feed it different lengths of text and it works fine. And then finally, we have the what we call E3 generalization. So that's when we apply, when we train on this whole system centered at the origin, and then we apply a test time transformation to the whole system. So it leads to a distribution shift, a mismatch between training and testing. And you see all the non-equivariant methods, they're very not robust to that. They perform very badly, and the equivariant ones are still working. So so this is, of course, a very simple problem, but it highlights, I think, some nice properties of this kind of method, both the equivariance and the transformer architecture. Then we have also some applications to the problem of arterial wall stress estimation. I won't go into the medical details, but it's an important diagnostic tool. And it can, again, just like with the physics examples, the chemistry examples, can be simulated, but it's very expensive. So you can use a machine learning method to predict it. And here too, we see that the geometric algebra transformer outperforms the non-equivariant transformer. Yeah, let me skip some of this. All right, then we get to robotic motion planning. I think this should be animated. Yeah, there we go. So this is a simulated robotics task. We're currently working on porting training the model in simulation and then actually running it in real life. We do that because even with these geometric methods, you still need quite a lot of samples, and doing that in real life will take forever. So we and many others are using simulators. So the task here is to simply stack blocks. Sometimes just have to make a stack. Sometimes you have to do it in a specific order, depending on the particular task. Yeah, it's done in simulation with something called PyBullet. And the general method that we used was proposed in this paper by GATr et al. Last year, which is based on a diffusion model. So diffusion models, if you hadn't heard of it, they're behind the recent generative image models that have been so successful, like stable diffusion. And the general principle behind a diffusion model is you start with some noise, and then you have a neural network that gradually denoises it until you get a sharp sample, which could be an image. But the proposal of this paper was to say we're going to apply the generative models not to images, but to robot trajectories. So a robot trajectory has, time steps and some variables that encode the state of the robot. And as the robot is doing its thing, it's stacking the blocks, those variables, of course, change. So you can think of it, you can also represent it as a 2D image that is one axis of time and one axis the variables of the robot state. And then you learn a diffusion model of this based on a data set of expert trajectories. So you have either an human operator moving the robot doing certain tasks, or you have another policy that has already learned it. And from this data set, of this offline data set of trajectories, you can then learn a diffusion model and use that to plan a trajectory. So it's an imitation learning setting. We train on 10,000 expert trajectories consisting of states and actions, but there's no reward. There's just implicitly the assumption these trajectories are how you should do the task. And then instead of using the standard diffusion model, we use the equivariant GATr architecture as the denoising network in this model. And here we have the results. Again, what we're plotting is on the x-axis, the size of the data set. So as I mentioned before, data efficiency is super important in this type of application because it's very expensive to let a real robot do its thing. And simulation, you can get quite a lot of data, but you probably still need to fine-tune on real data because of the simulation and real-world mismatch. And well, we have our the original diffuser results here, and then we have our version of that method where we plug in a transformer, because in the original diffuser work they used a different kind of neural network as the denoising network. So we want to make a fair comparison. So we have a transformer baseline in orange, and then we have our GATr diffuser. And yeah, in this case, higher is better. So reward here measures the percentage of trials where the robot was successful in stacking the blocks. So you see the field isn't quite there yet. We're closing up on 80%. But at least you can see clearly that our method is much more effective, especially in the low data regime. Then what's also very important in the age of big data is scalability. So scalability refers to being able to process very large amounts of data, for example, long sequences, or let's say very long robot trajectories, or whatever it may be. If you're doing something with molecules, there are some very big ones like proteins. And with some neural network architectures, you run into computational bottlenecks. And what we validate in this experiment is that the good scaling properties of the transformer that have enabled people to train these on massive amounts of text data from the internet, that they still hold for our adapted version. So you see both memory consumption in the top plot and the time taken on the bottom. And skimming over the details, if you can just compare the green and orange curve, you see that asymptotically they have the same kind of behavior. So that's very nice, and it's also unique among equivariant methods, because you see some other methods they really scale far worse. All right, so I mentioned we are currently working on getting this to actually run on a real robot. There's all sorts of challenges involved because this has to run at high frequency, has to run on low power hardware, and it has to have these data efficiency properties, because you can imagine it's quite annoying to do 10,000 trials guiding this robot how to pick up objects. What you see here is not our method yet. This is some classical computer vision, but we are working to set this up. So stay tuned. We will also, in the final version of the paper, we'll include more results on other tasks. So again, stay tuned. Okay, so to summarize, we introduced the Geometric Algebra Transformer, which is a general purpose and scalable architecture for geometric data. It takes into account geometric structure through these geometric algebra representations and equivariance. Can take lots of different kinds of geometric data as input. You can use one architecture for many tasks. It has the scalability and expressivity properties of transformers that make them so successful, and it achieves strong performance even with small amounts of data. So the paper was published as a workshop paper and is currently under review at NeurIPS. If you're interested in this area, I also recommend looking at some of the background on geometric algebra, as well as some other works that are starting to use geometric algebra in deep learning, or the prior work on planning using diffusion models. And with that, I'd like to thank you for your attention, and I'm happy to take questions.
Taco Cohen!